Hey everybody, my name is Abhay, and so today I'm going to be doing something a little different. So this is a little more of an expository class. I'm not going to be explaining everything in like too much detail. Um, I like I will be explaining things, but like not trying to teach them to you, but I'm going to be trying to show them to you. Um, the sort of an end goal for this class is to give insight to how the human ear works in a cool way, because you can actually use advanced mathematics to understand that better. So let's get started. Um, so first we're going to start with differential equations. We're going to basically be talking about differential equations and stuff around it for most of the class. Um, and delving into certain physics sort of things, because that helps give better intuition. And please interrupt me at any time if you have any questions or something like that. Just interrupt me, and that's fine. I'll be looking at the chat too, if that's what you're comfortable with. Okay, so differential equations are equations which have solutions as functions. So for example, a differential equation can look like this: dy by dt is equal to y. And the solution for this is y is equal to e power t, right? So this is the equation, right? And this is the solution. The solution is y as a function of t. Okay? That's the solution. Okay. I'm hoping that you all have a general idea of calculus, and if you don't, um, I'm not going to use any integration, by the way. Just okay, I might use a little integration, but it's not nothing too detailed. Okay, so this is what a differential equation is. That is it's something where the variable is a function, in this case y. Um, to be more precise, you can write this like that, and the solution is y as a function of t. You know, okay. Today in particular, we'll be talking mostly about second order linear uh, ODEs. ODEs are ordinary differential equations, so that's just like differential equations with dy's and stuff like that. So what does this mean? Okay, so I'll explain as this goes. So to come up with this equation, I want to use a little physics as inspiration. So basically, let's think about what happens when we're thinking about an equation for a pendulum, right? Or something like that. So let's take a spring, right? A spring has, you'll write an equation like this: ma is equal to minus kx. Force is equal to minus kx. Okay, if you've not seen this, this is the formula for minus kx is the formula for the spring force. That is, you know, if the spring is sort of like 2 units away from the mean position, the force that's going to be pulling it back is 2k. It's pulling it back in the opposite direction, so it's minus. Okay, that is, if you have a spring, right, and you pull it 2 meters, the spring is going to be pushing back to get back with force 2k, right? If this is true, yeah. So the equation is ma plus kx is equal to 0. Now acceleration is x differentiated twice. So you can write this as m d square x by dt square plus kx is equal to 0. And a common notation we use while solving differential equations is, if we usually it's with respect to time, right? We assume something is respect to time, or usually the variable we're differentiating with is obvious. So instead of writing this whole d square by dt square or whatever, we do something simpler. We put dots. So x differentiated twice has two dots on top, plus kx is equal to 0. Okay. Okay. So this is an example of a second order linear ODE. Why is this true? Second order means that the most x has been differentiated, the most number of times is 2. Okay, x has only been differentiated twice. Linear means none of these terms are squared. That doesn't happen, right? Um, yeah, none of that doesn't happen. Okay, so it's just to the power 1. That's what linear means. Okay, so we're going to be looking at certain equations like this. You'll notice that there's no first x differentiated once. The thing is, we can add that to there. Why, when does that come in the physical case? Well, whenever we have friction, usually friction is proportional to b into velocity. So friction, if we add friction into the mix, the equation will look something like that. Let's Okay, remember velocity is just x differentiated once. Okay, so this is sort of the intuition. Like this equation governs the spring. So if you can look at my camera, if I have a pendulum, something like that. If I just let a pendulum just go, this equation is what's governing. The solution to this equation governs how this pendulum is moving. Okay, a pendulum will have a similar equation. So will a spring. Any questions? Yes, no.
No.
Okay. So I'll move on. Okay. Now let's briefly look at solutions to certain equations like this. Okay. I'm not going to explain fully what sort of stuff we get, um, but I'll try to explain how we get the solutions and how do you get solutions for this. The idea to this is try x is equal to e alpha t. Just try it. Okay. The thing is that because differentiation of e to the power something still gives e to the power the same thing, maybe with some constant. Okay, and we get something really cool because plug this into the above equation. What do you get? You get alpha square m e to the power alpha t plus b alpha e to the power alpha t plus k e to the power alpha t is equal to 0. Because alpha comes out once here because it's differentiated once, and alpha square comes out twice here because it's differentiated twice. Okay, so this basically comes out. You can cancel the e power alpha t because that can't be 0. Um, so you basically get m alpha square plus b alpha plus k equals 0. So you sort of get two solutions for alpha. Okay. So in other words, you have x equals alpha t. You get two solutions for alpha. Let those be alpha 1 and alpha 2. Then we can actually write the general solution as this. Okay. What do I mean by this? Well, alpha 1 and alpha 2 are constants depending on the whatever we found. C1 and C2 are C1 and C2 are sort of like stuff that you know wait, okay, so I think I used the wrong terms here. C1 and alpha 1 and alpha 2 can instead be called in this case they're just the roots of this equation, right? And C1 and C2 are constants that will vary depending on the initial conditions. So for example, if we are given that um, initially we're given that x0 is equal to 0 and x dot 0 is equal to 0. These are the initial conditions. Then you substitute in there, you get using this, we get C1 into 1 plus C2 into 1 is equal to 0. And using this, we get C1 alpha 1 plus C2 alpha 2 is equal to 0. And using these two equations, you can solve for C1 and C2. Okay. So this is sort of like how you find, there's a lot of stuff I'm not talking about, but this is sort of how you find the solution for this sort of an equation. Okay. Also, alpha 1 and alpha 2 need not be real. In the case that they're imaginary, you'll you guys know that this thing, right? Um, e power I theta is equal to cos theta plus I sin theta. Okay. So you can sort of use this, and instead of the solution being in the form of exponentials, you'll get something in the form of cosines and sines. If alpha 1 and alpha 2 are imaginary. If one of them is imaginary, of course, because they're the roots of this quadratic equation, the other one will also be imaginary. So you'll get something like this. So you'll get you'll get something of the form C1 cos alpha t um, plus C2 sine something like that. Okay. So if that's true. Okay. If you have any questions, again, please stop me. Yeah. So this is what we get. Okay. Now to make things more interesting, we're going to modify this equation even more, right? Um, we're going to modify this equation even more.
I have one
What
doubt.
we're going to do, yeah.
When that thing alpha comes out to be imaginary, like complex, I mean. So, but like x is equal to e to the power alpha t, like it's a function in alpha, right? It should be real, right? X should be real in general.
Oh, yeah. Okay. So let me explain that better. So I just skimmed over that. So what we're going to do instead there is when it can't be imaginary, of course, right? If alpha comes out to be imaginary, x can't be imaginary. The thing is that we can add them in such a way that they come out to be real. Okay. So here's the thing. Okay, you can go try this. I'm not going to explain this complete detail, but you can try this for yourself. So if when you expand this, you'll get something like C1 if let alpha 1 be equal to A plus BI, okay? Then in that case, alpha 2 is going to be A minus BI, correct? So if you expand that, if you expand this, then you'll get A is equal to, so X is equal to, X is real, but for now, just bear with me writing like this. C1, um, so E power A will just come out. Okay, let me just write this fully. E plus BI T plus C2 into E power A minus BI T. Um, so this is going to be C1 E power A cos BT plus I sin BT plus C2 E power A cos BT minus I sin BT. Okay, so you get something along the lines of C E power A C1 minus C2 cos B power T
Shouldn't it
plus,
be a to the power 80?
oh yeah, I'm sorry about that. Thank you. This is C1 plus C2, right? Yeah. C1 minus C2 sin dt. Okay. So yeah, e power 80. So the thing is, if you sort of substitute this in the original equation, both of these still have to work. And also, just to be clear, we are wanting x to be real because we got this from physics or whatever. But 1 second, that's still not, yeah, okay. This equation, we want that to be real, x to be real because we want this to be physics, but it doesn't need to be real. Okay, I'm just putting it out there that x can be an imaginary thing. Um, but anyway, coming back to this.
But
So
it can't be imaginary because that equation was from physics only. No?
yeah, true. So okay, so let me do something else instead. So what we can do instead is say introduce a new variable z, right? Such that z is equal to real x. Sorry, x is equal to the real part of z. Okay, and then say we're gonna be doing this. We're gonna be using this trick later also, and then say solve for this equation where z can be a constant, and take whatever real part you want out. Okay. Anyway, coming back to this. So C1 plus C2 and C1 minus C2 are again random constants because, for any of these values you can solve for the others. Um, so what you end up getting is, so when you substitute this into the original equation, the I doesn't change, right? The I sort of acts like a placeholder. Okay, so when you differentiate this once or twice or whatever, the I stays the same. Okay, the I sort of acts like, like if you add 2 plus 3i and 4 plus 5i, the 2 and the 4 add and the 3 and the 5 add, but they can never interact, if you know what I'm saying. So in the same way, here you can write the solution as c1 e to the power at cos bt plus okay, I c2 e to the power at. Let's hold these different for now. And each of these, this is a solution on its own, and this is a solution on its own. So for in the case where they're imaginary, you can actually write solutions like this: C1 a to the power dt um, um, plus C2 into this way. Does that sort of make sense? You can go and substitute this in the original equation and check um, that you still get the solution. If the solutions to the quadratic equation are a plus bi, then these will satisfy the equation. Does that make sense? Sort
Yeah.
bad explanation? I think it was. But don't worry, this won't matter too much. There's also, like, for example, you might also notice that I also missed the case where the solutions are equal, in which case you can actually make up another solution somehow. But let's not go there. Okay. So what is important? Okay. So like I just said a bunch of stuff which might be very confusing. So I just want to reiterate what is important, that the differential equation of this form um, this, okay, you can solve it. Um, you can find the solutions to such an equation, okay, and this solution has something of the form, either in exponentials or cosines and sines, okay, and you have some constants which depend on the opening, the starting conditions, the boundary conditions, okay. Don't worry too much about the exact solutions and stuff like that. Now we're going to do something different. We're going to add something called a forcing term. What is that? Basically, we're going to add f of x on the f of t on this side. Okay, what is this f of t? It's like an additional force. So if this is the pendulum that I was describing earlier, if you can look at my camera, um, before I just left it and just let it oscillate on its own. Now I'm sort of moving my hand, adding an additional force. Okay, so remember that if we are going to compare this to physics, the MA, BX, and K, so BX, BV, KX, these are all forces. So we're adding an additional force that doesn't depend on X. It's sort of like it's doing its own thing. Wherever X is, it does. Wherever the pendulum is, it doesn't matter. It's doing its own thing. So if I'm moving my hand, then that's what this f of t is doing. Okay. Um, so we're going to be interested in a lot of different FTs, but one of the most important FTs, especially even for the ear, is something that oscillates like a cosine or a sine. That is basically, what I just showed. My hand is moving back and forth and back and forth. In that case, look, the force that I'm applying is, changing directions like a cosine or a sine wave. So we're going to be mostly interested in the case where ft is of the form cos omega t or something like that. But I'll show you how to expand this later in a minute. Okay. The thing is, this becomes much easier to solve. Remember the process where we just guess ex equals to a alpha t, add something like alpha t, and things became much simpler, right? We were able to sort of find the solution very quickly. So what we're going to do to make this simpler with that in mind is we're going to use the same trick I just mentioned, where we're going to introduce a z Well, the real part of z is actually x. We don't care about the imaginary part of z, but we're adding it for convenience. So what we actually want to solve is we're adding a z there. Okay, and we can make it this e power I omega t on this side because the real part of that is cos omega t. The real part of this z is x. So the real part of this equation is nothing but that equation, which is what we want to solve. But this is actually simpler to solve. Okay? Using complex numbers makes this simpler to solve because exponentials are like really cool when it comes to differentiation. They sort of simplify really easily. Um, okay, this time like I'm not going to go too deep into how we get the solution, but yeah, let me not go too deep into that. But um, here is what you can check. The solution is of this form. Yeah, it's nothing too complicated. Okay, so Let's say. So I'm gonna call something called a characteristic polynomial. Say GZ. Say let me choose a different variable there. Say G of R as mr squared plus br plus k. Okay, basically this. So that's exactly what we're going to get if we're going to try substituting something like e power alpha t into this equation. Okay, and then you'll notice that you differentiate twice and differentiate once and stuff, and then you get this equation like you get g alpha into e power alpha t is equal to e power I omega t. If we guess z is equal to e power alpha t as the solution, okay, something like that. Okay, so you can try that out by yourself. I'm not going to go too much into the details. And it turns out the solution to this is z is equal to e power I omega t by g of I omega. Okay. I'm sorry like that I have to just tell the solution, but you can actually go ahead and check this works, right? For example, you can put it in here and differentiate once, differentiate twice, and just substitute and see that this actually works. It's pretty straightforward. It comes out very easily because the bottom part is just like a constant basically. It has no t dependence. There's no time in there. It's just a constant, and this sort of you bring this comes out, something comes out, and that cancels with this and equals. Let me not go. The point is that this is the solution. This is a solution to this equation. Okay. Um, okay, so let's look at this for a certain case. Okay, let me look at this for a. Okay, I know I'm being too vague and confusing. So let's look at a certain case. Let's say, let's solve a certain case. Okay, I'm gonna ignore friction. Okay, something like that. All right. This is the equation that I'm differential equation that I'm choosing. It's basically something like this pendulum, but like we're ignoring friction. Um, and what I'm driving this with cos omega t. That is, I'm applying an external force which goes up and down, and that changes as cos omega t. Note that omega naught and omega are different constants. I'm choosing this random omega, okay, as my I can change this omega later. So I can move this quickly, and if I want it slowly, like I can do this slow. I can sort of like move this slowly, or I can move this quick. I can do whatever I want. So what is the solution according to what I said? So first we have to complexify. That is, we choose a z such that x is equal to the real part of z. So then we are actually solving this equation. Now, as I said, the solution to this equation is a solution to this equation. I'll come back to that later. There are more solutions, but this, like basically the important part, the other part doesn't matter much. So a solution to this equation is z is equal to e power I omega t by g I omega. And what is g over here? It is r square plus omega. right? Okay, because you just basically what you do is if you are differentiating the variable twice, you replace it by r square. You're differentiating it one time, you replace that by r, and if you differentiate it, nothing, it's just a constant. Um, okay, yeah. So the solution, the don't worry if you got confused by how you get the solution. Just know that the solution to this equation is this e power I omega t by omega naught square. Okay, since we substitute I omega here, that becomes minus omega square. So this becomes minus omega square. Okay, so this is a solution to this. Okay, now I want you to notice something very interesting about the solution. When omega naught is a constant that depends on the pendulum itself, like right, like if this were like we're deriving this in physics, we basically get this from ma plus kx equals 0. So basically, in this case, omega naught would be omega. Since we wrote an omega naught square, that's just convenience here. Okay, I probably missed this when I wrote this second time. So omega naught square, that's just basically convenience. um, so this is basically root of k by m, right? Because we're dividing by m, and then we divide by m. We're comparing with this equation basically, what I wrote above. Um, Something here, this cos omega t doesn't matter. Okay, so we're comparing. So omega naught is equal to root k by m, right? So k and m, which are all m is the mass of the pendulum or whatever. K is the it depends on the tension and stuff like that. So omega naught is like totally dependent on the system. You can't change that without like changing the system. What we can control is omega, which is how fast we you know alter the system. And something you'll notice about this specific solution, and by the way, you can totally just substitute this back and check just to see it's a solution. Um, something very interesting you'll notice about the solution is when omega is equal to omega naught, the solution blows up to infinity. Okay, so to get the real solution actually out of this, you need to, since x is equal to real z, since we said x is equal to real z, you take the real part of this, and so the real part of this is simply this denominator is real. Omega naught square and omega are all real, and to get the real part of the numerator, it's just the real part of ei omega t. Ei omega t is cos omega t plus I sin omega t, right? So the real part is just cos omega t by. Okay, so this is the solution. This is how x changes with time, right? If I start moving this pendulum, okay, my hands are moving up and down, up and left and right with frequency omega, then the solution to the equation will be this, right? The pendulum down over here will move with this, right? And you can sort of think as omega naught squared minus omega squared 1 by this as the amplitude, because see cos omega, what is cos omega t doing? It's just going back and forth. This sort of factor 1 by omega naught square minus omega square sort of sets the amplitude, because wherever that is minus and forth, cos is going to go between those two values. The maximum is going to be this, and the minimum is going to be minus omega square minus omega square. So this value 1 by omega naught square minus omega square is sort of the amplitude with which the pendulum is oscillating, because x is basically the position of the pendulum, and for this function 1 by omega naught square minus omega square is the amplitude with which it oscillates. Okay, so notice that if omega naught square is equal to omega square, the amplitude blows up. So if we write amplitude, this function, okay, as a function of omega, it will go something like this. Okay, it will go up somewhere in the middle and it will go down. Then this phenomenon where the amplitude is maximum some intermediate value of omega, and I'll give you a demonstration in a minute, is called resonance. Okay, so it's sort of an intuitive thing. So you can look at my screen now. Hopefully you can see my screen, and I have a sort of a makeshift pendulum in the form of this charge. You can go try this out. If I move, okay, so I'll give it like zero, zero initial conditions, not moving. Um, if I move it like really slowly, that is very small omega. Even the amplitude is very small, right? Of course, I'm not moving it much, right? If I move it really, really quickly, okay, now I'm moving it very, very quickly, the pendulum is hardly moving at all. It's still not moving, right? Why is that true? Because I'm basically just pulling it back before it can even go in the direction I just pushed it before, right? I'm pulling it. I'm vibrating it really fast. Okay, it's just look at the amplitude of the pendulum. It's not moving much, right? But if I choose the right amplitude, right? Well, this is basically intuitive. You've all seen this. If I choose the right amplitude, if I choose the right frequency for my hand, I'm sorry. If I choose the right frequency for my hand, okay, that is the driving frequency. I choose the right omega, it'll go really, really long. So the frequency that's like not too slow or too fast gives the highest amplitude. This is what resonance is. Okay. Any questions?
If we take like omega equal to omega naught, it means that the amplitude is basically infinite. Right?
Right, right. But if we add friction, it won't. It will be still be really high. So actually, okay, wait 1 second. I'll just if we add friction, if that B term is there, the solution will look something like this. Um, omega naught, omega t minus some phi, some constant phi over here, and plus b square. Right? If the friction was some b into something. So this is how the this square. Right? This is how the solution will look. So still, since b is a constant, the solution will still max at omega is equal to omega naught. It will look like this. So it won't go to infinity, but it will still max out there. Yeah, go on. Prem.
Oh, okay, yeah, fine, okay.
Yeah. So if we actually have no friction, that is the case we like just saw. This no friction case, then the solution will actually look like there'll be a asymptoted omega is equal to omega.
Wait, but how can amplitude be infinite? Like a pendulum can only rotate in a circle, right? So it can be at max
Yeah.
2 pi.
Yeah. In this case, it will simply keep going and going and going in the same direction.
Oh,
If that makes sense. Yeah. Okay. Yeah, because in the case of a pendulum, like we're not actually measuring x, we're measuring theta. It's this is simple all this is simple harmonic motion, by the way. All these differential equations, everything is describing simple harmonic motion. And in the case of a pendulum, the simple harmonic motion is like we're not actually doing it with respect to x, we're doing it with respect to theta. Okay, so theta keeps increasing. That makes sense. Any questions?
Yeah. So in the case of omega is omega naught, the solution wouldn't be periodic, would it? Like,
Oh no, no, no. The solution will not be periodic. We just like this is singularity solution. Of course, we need to solve it differently when this solution is only true for omega not equal to omega. We need to solve it differently, but the fact that the solution is not periodic and acts very differently still holds.
okay.
Any other questions? Okay, so moving on. So the next thing I want to talk about is um, so we had a solution, something of the form. We are looking at something of the form this. Okay, and because we actually generally looked for the case where this was an exponential, not cost, but like anything which can be written in the form of exponential, cosine, sines, any exponential function. Um, we can solve anything like that. The thing is, what if we want to solve more general functions? And we generally look for the case when the forcing term is periodic because that's what we care about. This generally is something simple, something simple harmonic. And there's not many cases of interest where the right-hand side, the forcing term is not periodic. Oh wait, I'm sorry, I forgot to mention one more thing. Notice that this solution is a wave with frequency omega. Okay, that is, the frequency of the solution is the frequency of the forcing term. Okay, which might not sound like much, but the fact is that it doesn't. Okay, so the solution always will just end up oscillating with the frequency which we are you know oscillating it with. Like, it doesn't sort of act with a different frequency, behave. It doesn't respond with a different frequency. It just responds with the same frequency. And the second thing I forgot to mention is that indeed what I said above is not actually the complete solution, though it's all that actually matters. So for such a for such a case, we can actually split x into, for the solution, if x is equal to something that's the solution, we can split that something into two parts: the particular solution and the homogeneous solution. Okay, the particular solution is what we found above. The homogeneous solution is what we found when we are looking at the case when this is 0, right? So basically, just substitute this equal to 0, and whatever solution you get is homogeneous solution. And there are two constants in that solution, remember? So you get you probably will get something like this. Okay, you probably end up getting like this, x particular, but this. And the reason I'm saying that the homogeneous solution doesn't matter, so for one thing, note that the x particular is just like a particular solution, right? The homogeneous solution, on the other hand, has constants that will change depending on the initial conditions. But the homogeneous solution doesn't matter much, because especially for the case that we're looking for, usually what ends up happening is R1 and R2 end up being negative real numbers. So they sort of decay away, and this just ends up vanishing after some point. It becomes insignificant. So the initial conditions don't actually matter, and all the solutions will end up being acting like the particular solution after a certain point. Okay. And it is true that you can write any solution to this equation of this form. Okay, though I will not prove that. And why did I say R1 and R2 are generally negative real numbers? Well, you can look at the case. Well, you can look at the equation that we are handling. Sorry, not kx. Mx dot dot plus kx dot. Sorry, wrong column. We usually write a b over here, constant, and kx is equal to 0. And remember that R1 and R2 are solutions of the equation this. If you don't, that's fine. Okay, this is not that important. Okay, this and k, b, and m are all positive real numbers, and because of this, you can show that the sum is minus b by m, which is a negative number, and the product is k by m, which is a positive number. So this means that the roots of field are both negative numbers. Okay. So the particular solution that we found now, something of this form, is what actually ends up happening for all initial conditions after a while. Like wherever you start, it just ends up oscillating with frequency omega, which is what we're driving which is what we're moving it with. The homogeneous solution just sort of decays away after a while, right? It becomes insignificant. Okay. So the lesson there is don't worry. I'm just telling you that the homogeneous solution also exists in very general cases where these can be negative numbers. They don't have physical meaning generally when that happens. But if you want, then this is like the entire solution. Where depending on like an opening condition, the initial position and initial velocity, maybe you can determine C1 and C2 and find the exact solution. Okay. Yeah, okay. So coming back. Something like this. The idea to expand to more complicated functions is something like if we want to solve for general functions on this side, not only cos or exponentials, the idea is to use something called a Fourier series, which I'll briefly explain. But you should know, whatever, like even if you're not able to completely follow me, that the general idea of a Fourier series is to write any periodic function. For now, we're gonna assume that ft is like a period, function of period 2 pi, but you can all just easily scale that, so don't worry too much about that. Ft can be written of the form a naught plus okay. That is, you can write a periodic function as the form a naught plus a1 cos t plus a2 cos 2t plus a3 cos 3t till infinity, and then b plus b1 sin t plus b2 sin 2t plus b3 sin 3t, when all these ai's and bi's are constants that you have to determine based on the function. So the point is that if we want to write the function of this form, you need to be able to find these ai's, right? And the way you do that, and note why this is so useful, right? If you have some general periodic function over here, right? Um, I think it's a little laggy. I'm sorry about that. Yeah, so if you have some AI, then once you substitute here, you can get something of the form, some constant plus AI cos I, some BI sin I, and okay, because of the fact that, so basically, if you have something like this, plus psi plus maybe sin 2 sin omega t, hey guys, can you hear me?
Yeah.
I'm sorry, my internet went away. Let me actually okay. Can you can any of you confirm that you can see the screen? Guys, can you see the screen?
Yeah.
Oh, great. Okay. So what I was saying is, was for something like this, you can actually split the solution. You can find the solution for this, and you can find the solution for this, and add them together. Okay. So if you have this, if the equation is ax dot dot plus bx dot plus c is equal to cos omega t plus 2 sin omega t, then you can sort of write the solution as x is equal to the solution when only cos omega t is there, and the solution for only 2 sin omega t is there. And you can prove this, right? Okay, so this would be the solution. Something like this would be the solution, 2 sine omega t something. So this being able to write a function as a Fourier series is very useful, because then you can just, like, it's very easy to find the solution when you do that. Okay. And so I'll briefly just explain how you get this Fourier series for a function. The idea is that, okay, I'm going to be using a little bit of integration for anybody who don't. If you don't know integration, this is not that integral. Okay, so I'm going to write down a few integrals. And you can tell me what you think. You can prove all these integrals, by the way. They're nice exercises. Okay. So this is the idea. The idea is that integrate cos nt sin nt, what n can be equal to m and m anything, from minus pi to I, any n, any m, the integral is 0. Integrate cos nt cos mt from minus pi to pi, where n and m are not equal, and the same for sin n and t. The both of those are still 0. Okay, these are this equal to. The only time when such an integral doesn't come out is when it's cos nt or sin nt sin nt, and if you integrate that from minus pi to pi, you get pi. Okay, and you can I hopefully it's somewhat obvious how you can use this here. What you do is just multiply. So say you want to find out n, right? Some certain an. So say a4. What do you do? That is, you want to find the coefficient in this equation of cos 4t. By the way, for those of you who have not seen something like this before, think of maybe if you've seen Taylor series, this is somewhat similar. Even in Taylor series, we want to find the coefficients of the polynomials, right? So the same way here, we want to find the coefficients of the cosines and the sines. Right. So how do we find a4? What do? We multiply both sides with cos 4t. Okay, and we integrate from minus pi to pi. Every single term on the right hand side over here, every single term integrates to 0 because of this. All the sine terms integrate to 0. All the other cosine terms, because see you have some. What happens to the cos 10t term? You have a10 cos 10t. What happens to that? Well, you're multiplying cos 4t cos 10t, and then you're integrating from minus pi to pi, and cos 4t cos 10t integration from minus pi to pi is 0. So everything else cancels out except this term. Okay, so you get some general formula for this in the form an is equal to, well, on the left hand side we have this. You're multiplying by cos nt, you're integrating from minus pi to pi, and here note that you'll also have a pi, so you actually have to make this 1 by pi. Okay, because the pi comes from integrating minus pi to pi cos 4t twice, right? Because this pi, right? And bn is very similar, the same thing, but sin. Okay, so the general idea of a Fourier series, okay, and this actually some 3 blue 1 brown is a pretty good. He uses a slightly different way where he uses exponentials instead of talking about sines and cosines directly, but you can see that they're actually like pretty much the same thing. You can go check that out. Yeah, okay. What was I saying? Right. So you can split any function f of t in the form of cosines and sines, with many frequencies. Okay, so with that detour, let's come back to the last part, the second last part of this sort of talk. Okay, let's say ft is of that form as we saw. What is it? A naught plus n equals 1 to infinity an cos nt plus sigma n equals 1 to bn cos sin nt. By the way, I'm really sorry about my disgusting handwriting. Okay, then, and let's say we now have a function where the forcing term is ft above. This is the forcing term. Okay, that is, we're moving our hand in the case as a function of time as this. That's the force we're applying. Then our differential equation is let's just keep the right constants. just to let me just write a M and the B and a K over there. Okay. What is the solution going to be? Well, we'll split it into the cosines and sines, and we know the solution for each cosine and sine. We've found that out before. We're going to ignore the homogeneous solution. Remember, we're only going to care for the particular solution, which is what's going to happen anyway. So if we have something like this, how is x going to change with time? Well, the solution is, okay, the solution is this, something like that. When we have, I'm also just going to ignore the constant for now for reasons. Let's just not complicate this. Let's keep them simple. This constant term. Okay, I'm just going to ignore this one over here. So the solution we get is x is equal to an cos nt by n squared minus omega squared, right? Because n is basically did I say something wrong? I think I'll give me a second. I didn't use omega naught squared, so let me just, okay. Let's use this equation instead. I'm basically replacing omega naught with that. And okay, so what happens is, the reason I'm hesitating here is that adding friction here complicates things a little. Like last time, that's why I did not have the friction term and only told you later. And I'm going to do the same thing here, right? Let's just act as if friction doesn't exist for now. Okay, I'm really sorry about that. So this is the differential equation we're going to be talking about. Okay, and the solution for this differential equation is for each cost term. So let's say you have a certain cost term, cos 40, right? Let's say you have cos 40 and you have you know A4. We found out A4 because we know FP. We found out A4. Then the solution for that particular part would be A4 cos 40. We know A4, it's a constant. So, I'm just going to write that, but know that it's a constant that we have found out, into divided by 4 square minus omega naught square, right? This is exactly the same thing we found out when we only had one cosine term. Remember, it was cos omega t by omega, okay, it was omega naught square by omega square. So this is actually that negative of this. Right. Anyway, this is the solution. So right, it's the exact same solution, but in this case, since we have many terms, we're going to have to add all those solutions up to get the final solution. Right. So the solution is going to be this from n equals 1 to infinity, omega naught square minus n square. The same for the sine terms. This is still going to exhibit some sort of resonance. Okay. This is still going to exhibit some sort of resonance because, for example, look at this. What if, okay, this is sort of something in a different way. What if omega naught, okay, this depends only on the system, remember, omega naught changes depending on the system, was very close to 3. Then only the 3 term, the third cos 3t term and the sine 3t term will have abnormally high values, right? So since if omega naught is very, say, close to 3, 3 squared, let's say 3 squared, because that only that specific term will oscillate. Like the amplitude of that specific oscillation. So in this case, 3 or 9 will have higher amplitude, right? That will dominate the rest of the terms. Okay, do you people understand that? So if, for example, omega naught squared, if omega is really close to, let's just say 3 in this case, then the cos 3t term will be really high. Okay, and it will dominate the rest of the terms, which means the entire solution will almost be behaving. There'll be irregularities, but let's look at the limit. It will almost be behaving like um, a function of with the frequency itself, right? Does any okay? Does anybody have any questions? Okay, we have one last part to the year. So before that, we can finally know enough to explain how the year works. Any questions before?
Uh, wait, so like in this case, we have that if omega naught is almost 3, the solution is like almost cos 3t. But what if omega naught is not a natural number? Say then uh, like why are natural numbers special in this case? Because omega naught can be any real number, right? So why is it
They're
that?
not special. They're not special. The thing is that there are you actually have you could sorry. Yeah, you will actually end up having something like you won't have nt, right? You'll actually have something along the lines of n omega t for some random omega, and then you'll have n omega square whole square here, which I conveniently ignored that omega um, as a general solution. Okay, so the thing is, okay, I get what you're asking. You're asking why natural numbers are special here. The reason we didn't have this omega so far is because we're assuming that our function ft has a period of 2 pi, right? If it has a period of 2 pi, then natural number frequencies become special because we can write the function as a form of cos t plus cos 2t plus cos 3t. If the function has a different period, then we won't be able to write it properly as a function of cos t plus something cos t plus something cos 2t. We'll instead write it as something like cos x something like like if it has, for example, a period of 4 pi instead of 2 pi, then we will we'll write a1 cos t by 2 plus a2 cos t plus a3 cos 2 3t by 2. Like, do you get what I'm saying? In this case,
Yeah,
these are
okay,
special, but that's only because we're choosing ft to be very something very specific period of 2 pi.
okay, yeah, got it.
Any other questions? No? Okay. Okay. So finally, what this talk was supposed to be about, the year. It's basically exactly what I just said. The thing is, in the year, I don't know the exact position and the name of the things. There's this, there's this sort of round thingy where after the eardrum, I think it's in the bones, um, in those small bones. There's like a lot of hairs. Okay, and these hairs, okay, are all of different sizes. Like there are many hairs of many different sizes. Okay, and they have different weights, thickness, and things like that. Now, because of their different sizes, they have different values for omega naught. Okay, remember, omega naught is something like root k by m. Okay, k is like sort of depends on the stiffness, m is the mass. So this depends on the string itself. Like, you can't change this um, k and m, right, after the system is made, like without changing the system. And in this case, what the hairs are going to be doing, the hairs are going to be moving back and forth. And like depending on how back and forth they move, they're going to be sending signals to the nerves. Okay. And in this case, sound that's going to be coming into our ear is the force field, right? The sound is basically what oscillation in the air, and the ear amplifies these sounds so that the sound sort of comes and moves the hairs around, right? Now, the sound we hear is of different frequencies. There's so many different frequencies going around, but somehow we're able to differentiate between these. Okay, what a computer does to recognize certain sounds is a computer can recognize, like if it hears sound, it's able to recognize what those sounds are, right? It basically calculates the Fourier series, right? It it uses the methods we described above. Okay, a computer does this, right? It does this where it knows the function, it's given the function because it hears the function, it hears the sound. And what the computer does, it uses these formulas to calculate, it does all these integrations, it finds out the values for you know an, and so it gets the frequencies, it gets all the cos omega t's. But somehow our brain is able to do the same thing. That is, if I'm if I'm able to like make two sounds of very different frequencies, the brain is actually able to distinguish between them. Like that, you'll be able to hear two different voices. Okay, when there are different people talking, you're able to differentiate between their voices, you're able to break them down into different voices, right? which is pretty cool. And we're pretty, our brain doesn't do the integration somehow. So what does it do? So it does this, where it has different hairs, right? And all the hairs are different omega naughts, right? They have different KYM, and each of those is a system. A hair can exhibit sort of simple harmonic motion where it moves back and forth and back and forth. And when the like let's say our brain, like there's a sound which has multiple frequencies. Let's say there's frequency of 2, 3, 5, some units, I don't know, hertz or something. Not hertz, because I'm not sure if we can hear these. I think we can only hear 20 hertz, 20,000. I don't know, let's say 20, 30, and 500 or something. Whatever, something hertz. We hear these. There are going to be hairs with omega naught equals 22, 30, and 500, right? Omega naught, there are going to be hairs with these omega naughts. And because each of them is having a simple harmonic motion equation, this equation, with ft as the sound, but ft will be something like cos 22t plus cos 30t plus cos 500t. Okay, and the solution, which is basically how the hair moves, is going to be something like this. The specific hair in the bone, which have omega naught equals 22, will move with the highest amplitude. So they will send the strongest signals. And similarly, the hair somewhere over here, the ones with, the hair with 22 will be here, the hair with 500 will be here, the hair with 30 hertz will be here. And these hairs will send the strongest signals because they're moving the most, because of this resonance, right? Because their omega naught is very close to one of the omegas that the FT has. So these omegas, those specific hairs will move the most. And in this way, the brain can tell exactly what frequencies the sound, the sound contains, which I think is pretty cool, right? This sort of like how the ear works. The eardrum and stuff, they amplify the sound, and the amplified sound acts like the force, right? It vibrates the liquid or whatever inside, and it goes and vibrates the air, and the hairs that move the most and the strongest signal. So any questions? That was basically supposed to be my lecture for the day. That's supposed to be my talk. Any questions? Anything we can explain? Any questions? Feel free to ask it. But even if you're not able to understand something random, feel free to ask.
So basically, there is a hair for each frequency.
There is
A hair for each frequency.
for every frequency that we can hear. We can't hear every frequency. Remember that. I think the human audible range is 20 hertz to 20,000 hertz, something like that. Somebody correct me if I'm wrong.
Yeah.
Yeah, so like everything below is ultrasonic, everything ultrasonic. So basically, our hair frequency depends on what hairs we have in some sense. So everything, like we don't have hairs below 20 hertz, so that's why we can't hear those sounds. If that makes sense.
And there are hairs of only natural number frequency.
No. Their hairs are like like it's the biology is not exact, but natural numbers don't. As I said, I just said natural numbers don't matter that much. In this case, natural numbers seem to matter because the FT, the solution came out that way. So because FT, if FT is assumed to be a function of a period 2 pi, then the solutions will the frequencies which will have the most impact will be natural numbers. But like even if omega naught is not exactly like 3.4, if it's something like 3.889, it will still oscillate most to when the sound has a frequency 4, compared to like a omega naught of hair with frequency 10, if that makes sense. So like there won't be exact natural frequencies, the hairs. The hairs will be of many different intermediate things. Like there'll be one 3.1, then there might be one 3.105, but then the next one may be 3.3. Like in some sense, the hairs will be random, but they'll get the job done because some of them will move more than the others, and the brain will be able to tell because of which hairs move the most.
I see.
I'm extremely sorry, guys, and this was very confusing. Um, yeah, I'm sorry about that. So I think we can stop the recorder.